It doesn't look dangerous. It doesn't glow in the dark the way movies tell you it does. It is dull, silvery white, heavy in the hand. And yet, locked inside it is a force so absolute that a single kilogram of it holds the energy of 1.5 million kilograms of coal. Its name is uranium, element 92, the heaviest naturally occurring atom on the periodic table. And it has shaped science, history, war, and the future of our civilization in ways we are still reckoning with today. Berlin, 1789. A German chemist named Martin Heinrich Klaproth is dissolving a black, heavy mineral, pitchblende, in nitric acid. He adds potash, and what he observes does not match any known element. The reactions are wrong. The precipitate is wrong. Everything about this substance is wrong. He concludes he has found something new. He names it uranium, after Uranus, the planet discovered just 8 years prior. But Klaproth has not actually isolated the element. He has only glimpsed it. It will take another 50 years and a French chemist named Eugene Pelligot to finally hold pure uranium metal in human hands. And here is the detail that stops every historian cold. Uranium oxide had been in use since at least 79 AD, decorating Roman glass and ceramics with its vivid yellow-green tint. For nearly 1,800 years, humanity painted with an element it did not understand and could not have imagined.
Then, in 1896, a French physicist named Henri Becquerel left a sample of uranium salts resting on a photographic plate, planning to study how sunlight activated its properties. The skies that week were overcast. The experiment was shelved. But when he developed the plate anyway, it was fogged, exposed, as if by invisible light. The uranium had done something on its own, without sunlight, without any external energy whatsoever. Becquerel had stumbled into radioactivity. The atom, science had assumed, was the end of the story. Uranium had just rewritten the opening chapter. Inside every uranium atom sits a nucleus of extraordinary density, 92 protons, between 141 and 146 neutrons, depending on the isotope. And it is that word, isotope, that explains everything. Uranium exists in nature as 3 isotopes. Uranium-238 makes up over 99% of all naturally occurring uranium. Its half-life is 4.5 billion years, roughly the age of the Earth itself. It decays, slowly, imperceptibly, and in doing so, it heats the planet's core, drives continental drift, and keeps this world geologically alive. And then there is uranium-235, a fraction, just 0.72% of all natural uranium, barely a trace, and yet it is the hinge upon which the entire nuclear age swings. Because uranium-235 is the only naturally occurring isotope on Earth capable of sustaining a nuclear chain reaction. Here is what that means. Fire a single neutron at a uranium-235 nucleus. The nucleus absorbs it, becomes unstable, and splits. 2 smaller atoms are born. Energy radiates outward, and crucially, more neutrons fly free. Those neutrons strike other uranium-235 atoms. They split. More neutrons, more energy, more fissions. In a fraction of a second, a chain reaction can cascade through millions of atoms, releasing energy millions of times more powerful than any chemical explosion ever ignited. By 1939, the world was at war, and 2 facts had just become terrifyingly clear to physicists on both sides of the conflict. First, uranium could be split to release catastrophic energy. Second, whoever achieved that first would win everything. The Manhattan Project mobilized thousands of scientists across secret facilities in New Mexico, Tennessee, and Washington state. They worked in absolute secrecy. They raced against a deadline that was not a deadline. It was history itself. On the morning of August 6, 1945, a uranium bomb called Little Boy was released over Hiroshima, Japan. It detonated at 1,900 feet. The fireball reached temperatures hotter than the surface of the sun. An estimated 70,000 people were killed instantly. Tens of thousands more died from burns and radiation in the weeks that followed. The same physics, the same element, a different intention. Today, controlled uranium fission powers the electricity running through homes, hospitals, and cities across more than 30 countries. Over 440 nuclear reactors operate worldwide, generating roughly 10% of all global electricity, with no direct carbon emissions. Inside a reactor, uranium is formed into ceramic pellets, each one the size of a fingertip.
Each one capable of producing as much energy as 17,000 cubic feet of natural gas. They are stacked inside fuel rods, submerged in water, and set into a controlled chain reaction. The heat turns water to steam. The steam drives turbines. The turbines produce electricity. Clean, continuous, reliable. And yet, uranium's reputation carries a shadow that no reactor output, no carbon comparison, no safety statistic has ever fully dissolved. Because the disasters are real. In 1986, reactor number 4 at Chernobyl exploded, releasing radiation equivalent to 400 times the bomb dropped on Hiroshima, contaminating 77,000 square miles of Europe. In 2011, a tsunami crippled the Fukushima plant in Japan, forcing the evacuation of 150,000 people. These are not footnotes. They are defining events. Events that reshaped energy policy across entire continents, that closed plants, that turned public opinion, that made the word nuclear into something that ends conversations rather than starts them. There is also the question of what happens before uranium reaches a reactor. Mining it is not clean. Processing it generates radioactive mill tailings, waste that can leach into groundwater for centuries. Communities near uranium mines, disproportionately indigenous communities in the American Southwest, in Niger, in Namibia, have lived with the health consequences for generations. And then there is depleted uranium, the byproduct left over after enrichment. Dense, hard, and radioactive, it has been used in armor-piercing military rounds. When those rounds strike their targets, they vaporize into toxic dust, a legacy that settles into soil and bodies long after any conflict has ended. The planet is warming. The window to act is narrowing. And the honest truth that climate scientists and energy engineers increasingly agree on is this: there is no credible path to a carbon-neutral civilization that does not involve nuclear power. Solar and wind are intermittent. Batteries cannot yet store enough. The grid needs baseload, steady, reliable, always-on power. And uranium is the only proven source capable of delivering it at scale without burning anything.
A new generation of nuclear technology is now emerging. Small modular reactors, compact, factory-built, designed with passive safety systems that cannot melt down the way Chernobyl did. Thorium reactors that produce far less long-lived waste. And on the furthest frontier, fusion, the attempt to replicate the process of the sun itself, using hydrogen rather than uranium, with the potential to make the energy question obsolete entirely. Uranium will not solve everything, but dismissing it entirely, as some nations have, may be the most expensive energy decision of the 21st century. The element does not care about politics. It simply holds its energy, patient and ancient, waiting for us to decide what we are willing to do. Here is the fact that reframes everything. Uranium was not made on Earth. It was forged in the hearts of dying stars, supernovae that collapsed and exploded 6 billion years before our sun existed. Their remnants scattered across space, fell through time, gathered into rock and dust, and eventually became the planet beneath your feet. For 4.5 billion years, uranium has been here, warming this world from the inside, patient and invisible, slowly releasing the energy of stars. And for barely 100 years, a breath of geological time, we have held it in our hands. We have split its atoms. We have lit cities with its energy. We have used it to end a war and to threaten the next one. We have watched it melt down,
and we have watched it decade after decade inside plants that most people never think about. Uranium does not ask for our wisdom. It simply waits, as it has always waited, with the patience of something older than the sun. The question it leaves us with is not whether this power is real. We have seen with terrible clarity that it is. The question is whether we are, at last, wise enough to deserve it.